Hello, welcome back. Today we go into the non-linear reduction recurrence relations, which is a part of our ongoing DAA series. In the last lecture, and you'll find it in the playlist, we had covered linear reduction recurrence relations, and today we'll cover non-linear reduction recurrence relations. And don't worry, we'll cover a bit of recap of the linear reduction recurrence relations, try to explain what's the difference between linear and non-linear reduction recurrence relations. We'll adopt the same approach as we adopted last time, which is typically around your recurrence tree format of solving recurrence relations, as well as substitution method of solving recurrence relations. So we will be doing this part of the syllabus now, which is on the substitution method and recurrence method. We are continuing from the last lecture and trying to cover this part of the syllabus, which we covered last time in terms of linear reduction. Now we'll cover it in terms of non-linear reduction. So that being said, we do these things today, which is the linear reduction recurrence relation, the non-linear recurrence reduction recurrence relations, which will fall under mainly two categories, which is divide and conquer relations as well as transform relations. And we'll try to cover these two, and there are many more categories, but these two are most important from your syllabus perspective as well as from your examination perspective, which is why we are focusing more on the divide and conquer part of the recurrence relations and the transform relations, which is marked here. So on the divide and conquer, we'll be doing balanced and unbalanced recurrence relations. And then on the transform, we will cover one of the ways how we can transform recurrence relations. And then, of course, we'll wrap it up by solving the most common problems that come in your semester examinations. So from a from a perspective of, let's say, recollecting what linear reduction recurrence relations were, let me take a step back. Okay, let's try to figure out what is going to be the recurrence relation for this recursive problem. This is a recursive problem. Why? Because we have recursive call here. So this is no more an iterative problem. This is a recursive problem whose time complexity we can assume as Tn, right? And if this time complexity of this test function is Tn, then can we assume that this if will take, let's say, 1 unit of time, right? 1 unit of time. Again, if you don't understand units of time, time complexity, you'll have to watch my recap video from the DSA series, which I have already posted in the DAA playlist, which would be the first video in this lecture series. On the for loop, we know that it will take n plus 1 units of time, right? And inside the for loop, anything will, if it is n plus 1, then inside the for loop, it will be n units of time. And the test n by 2 will be actually executing itself at Tn by 2 time complexity, and this will also be at Tn by 2 time complexity, right? So which means that because this was at Tn, which is at a value of n, so definitely when it is a value of n by 2, we will be taking Tn by 2 as the size of our sub problem. In any case, it denotes the time of executing that sub problem, or in other words, it could be a time represented by a function, it could be a time represented by a relation, or it could be a time represented by a theta notation, big O notation, gamma notation, which is basically your time complexity. So that is on this particular dissection of a particular piece of code in order to find out what are the individual lines of code complexities, or the way you want to call it, whether you want to call it complexities, whether you want to call it the time taken to complete that particular line, or whether you want to call it the recurrence relation Tn. It's up to you, right? So the time taken to actually execute this, if I add it up, then what do I get? I get Tn is equal to 2t n by 2, and then I will get 2t n by 2 plus 2n plus 2, right? Which means that I can simplify this further to 2t n by 2 plus I can say, let's say 2n plus 2 is again y equal to mx plus c. I don't need the constants, and hence from a time complexity, asymptotic time complexity perspective, I can very well say that this would be my recurrence relation. Why is this a recurrence relation? Because we are talking of a recurring problem here, right? We are talking of a recursive problem here. So there has to be a method to tell everyone that what is going to be the time complexity of this, right? Without even decoding the time complexity, without even finding out theta, without even finding out omega, without even finding out big O, can we write a relation which when solved will give us big O, which when solved will give us theta. You remember when we did linear relations, then we actually, or rather when we did a flat iterative polynomial kind of a time complexity, then we said that the highest degree of the polynomial is going to be the recurrence relation. So if we had actually found out that, let us say for an iterative problem, if we had found out that my time complexity Tn is equal to, let's say, n square plus 3n plus 2. Let us say that adding of the statements of an iterative problem gave us this time complexity. So if this is the case, of course it is not going to call itself, right? So that is why no calls of Tn minus 1, or for that matter Tn by 2, or for that matter Tn by 4, no calls of itself in a smaller scale or a reduced scale exists here for an iterative problem. So this call does not exist. What exists is this, which is the linear way of doing things without any recursive calls, right? So what would be the time complexity of this? The asymptotic time complexity, we were used to writing it as theta of n square, because that is what is the highest power of n, and that is what we had learned. Now when we convert, or when we shift our attention from an iterative problem to a recursive problem, then how do you express this equation? You express this equation by this, which is called as the recurrence relation, right? So this is why you call this as a recurrence relation, right? It is a recursive problem and you are trying to express this as a relation between the call of Tn versus the recursive calls, which is Tn by 2. This, Tn equal to 2Tn by 2 plus n, that is the recursive relation trying to tell us. Very simple. See, it is trying to tell us that there is a problem of size n, right? So let's say this is a problem of size n, which can only be solved if you solve two smaller subproblems of size what? Of size n by 2. Why two smaller subproblems? That is because we have 2Tn by 2 here, right? So that is why it is two smaller subproblems. Now each of these subproblems will be solved by doing how much amount of work? N by 2 amount of work. So these subproblems will be solved by doing n by 2 amount of work. Why n by 2? Because we have n here as the amount of work. This is the amount of work. You know it from the linear reduction relation that we had called out earlier. So from there you can understand what is work. So that is n work, which at n by 2 level becomes n by 2 work. So these two get done with n by 2 amount of cost, or n by 2 amount of work is done in order to solve these two smaller subproblems. At the next layer, these two further get broken down and they are forming two more subproblems, which says that these subproblems are of size n by 4, because each n by 2 is getting broken down into two smaller subproblems of size n by 4. That is, whatever is its current size, it gets broken down by half. N by 2 is its current size, it gets broken down by half. Hence, the work done here will be n by 4, because this n now becomes n by 4. The work done here is also n by 4. The work done here is also n by 4. And the work done here is also n by 4. Notice that the summation of the work done is n, which is actually equal to what you have here. Right? So this is what is happening in a recurrence tree. Now this is very clear when we talk about division. When we actually were doing the linear reduction recurrence tree, we were taking a recurrence relation like this: Tn equal to Tn minus 1 plus, let's say, some n we were taking. So what, or let's say, to keep it simple, let us take a constant here. Let's say we took it as 1. So what was happening is, we started off with Tn. We started off with a Tn as a recurrence tree, and in this recurrence tree, we said that we will have some work done, or rather some sub-problem, which will be actually, the size of that sub-problem will be Tn minus 1, or rather, let's call it like we had called it in the left side, we will call this as n minus 1. So the size of this problem, size of the original problem was n. Here also the size of the original problem was n, and we are solving this size by solving n minus 1 as the size of the sub-problem. And this sub-problem was taking to solve how much cost? 1 as a constant cost. Now to solve this n minus 1, we were also saying that we further go down and we solve n minus 1 minus 1, which is n minus 2, and that would take again a constant amount of work done, which is 1. In this way, we used to go down this particular tree and solve the total amount of work done, and that's what we had covered in the linear reduction problem. As you can see, this particular problem goes from here and then finally will reach a stage where the value of these reductions will come to probably 1, and at that point this will be our base condition where we will stop. This will be the base condition where we will stop. Here also, this n by 4 will constantly go down. This n by 4 will constantly come down, and at some point it will also become probably 1. This will also become 1. This will also become 1. This will also become 1, and that will be the base condition where it will stop. And this one may be 2, 3, 4, depending on the problem. These base conditions might change. So do you realize that in this particular example, let us say that in this particular example, do you realize that the n will reduce to 1 much faster than this example, where the n gradually reduces by 1, 1, 1, 1. Here n jumps by 2 every time, n reduces by 2, 2, 2, 2, and therefore it comes to 1 much faster. Then this actually goes to 1. So this will be a logarithmic complexity. Normally this will be an n order complexity normally, right? Our job is to find the complexity of such recurrence relation, drawing a tree like this and finding out what would be the theta of this particular sub problem. Also remember that the reason of breaking down this n into these two sub-problems is that solve these two sub-problems, you'll get a solution to this. But I don't know the solution of these two. So solve these 4 sub-problems, then you'll know the solution of these two. If you know the solution of these two, you know the solution of this. So this is how your recurrence tree works. Right? Here also the same thing. In the linear reduction recurrence tree, solve this, then you get to know this. Solve this, then you get to know this. And that's how it moves. So this is in a nutshell what we are talking about in terms of unit reduction recurrence tree or unit reduction recurrence relation to be solved using, let's say, recurrence tree. And then we also are talking about the divide and conquer recurrence relations, or we are actually talking about non-linear reduction recurrence relations to be solved using again the recurrence tree method. We can also solve it using the substitution method, but net what we are trying to get at is that this is a recurrence relation which is having a division, which means this is a non-linear recurrence relation. This is a recurrence relation which does not have any n divisions, right? Which means, or this rather, right, does not have, in fact this does not have any recurrence relation at all. This is not a recurrence relation at all. This is an iterative problem. Whereas this is a recurrence relation, yes, but this has a reduction factor of unity, which means this is a linear reduction recurrence relation and this is a non-linear reduction recurrence relation. I hope it's amply clear in terms of what we are trying to talk about here. Now, this table signifies what we are trying to cover, which is mostly around divide and conquer, which is a balanced way of dividing the main subproblem into smaller subproblems. So we are actually going to say that, okay, so you will have this will break down to 2 subproblems, and if you solve those 2 subproblems, you solve the bigger problem. This will break down to 2 more subproblems, and in this way we will also break down this into 2 more subproblems, right? So this is what is a balanced divide and conquer approach, right? There is an unbalanced divide and conquer approach also. So let us take that example too. So what we'll do is we'll say that this is the main subproblem or the main problem, and if we divide it in an unbalanced form, then let us say this is the subproblem, the inner subproblem, and that inner subproblem is not the same as another inner subproblem. So earlier these 2 subproblems were the same. They were, let's say, 2t n by 2 meant that this subproblem was n by 2 size, this subproblem was n by 2 size. Here these subproblems will not be the same. So this could be something like 2t n by 2 plus, let's say, n, something like this as tn, and this could be something as tn is equal to, we can write this as tn by 4 plus tn by 2 plus some constant k, right, which is the amount of work that is being done. So we are actually saying that, let's say, one subproblem is tn by 4 and the other subproblem is tn by 2. Let me write this cleanly. So we are saying that tn is equal to tn by 4 as one subproblem and then tn by 2 as another subproblem. The size of both these subproblems are different, right? So then the next chance that this will get, this will break down first in this side. It will break down, or rather let's take this one, this will break down into the tn by 4 subproblem, and this will break down, let me remove this and say that this will break down into the tn by 2 subproblem, and this on the other side will break down into this subproblem, which is tn by 4, and on the right it will break down into tn by 2. So every time a subproblem breaks, it will break down into by tn by 4 on the left and tn by 2 on the right. That means this is not the same percentage of works getting divided amongst the siblings, right? The siblings are doing different amount of work, which is why it is called unbalanced divide and conquer, right? So do you agree then that if the purple color or the red color, whatever you see on the screen, is actually n by 4 and the yellow is n by 2, then purple will be actually reaching a state of 1, much faster than the yellow will reach a state of 1. So yellow might be reaching a state of 1 here, which is the leaf of the tree, right? After that, no more divisions will be possible. So yellow must be reaching a stage here. So this part, please remember as we go forward in this session, that in an unbalanced tree, the part that will reach 1 may not be the same as the other siblings also, because the siblings are not broken down equally. They are not doing the same amount of work also. So which means that the subproblems might not be ending at the same amount of levels or the same amount of time. So the tn by 4, this being a larger division, will reach 1 faster, right? Then tn by 2, which is a smaller division, will take a longer amount of time to reach the leaf node or 1 node. That is what we can therefore summarize. The base condition for an unbalanced tree is not the same, right? The base condition for an unbalanced tree is not the same, right? Which means that one of them might be ending a particular problem at while it will be the same, or it may be the same with respect to saying T1 or T2, right? We can say T1 is equal to theta 1 or T2 is equal to theta 2. We can say that, but then it does not mean that by the time we get to T1, the subproblem 1 will have gone through the same number of levels as subproblem 2, right? Going to T1 does not mean that I have taken 10 steps of division of subproblem 1 and similarly 10 steps of division of subproblem 2, because subproblem 1 in this case will reach to T1 much faster because it is n by 4 or t by 4, tn by 4, and subproblem 2 is tn by 2. So that's what you need to remember from this unbalanced divide and conquer. So we have a lot of examples which we will try to cover, right? Some of them we will cover, and these are the examples I've taken. If you think about the first balanced subproblem, then this balanced subproblem, which is typically like this, is actually a part of your merge sort. You have done merge sort, and we will cover merge sort again from a DAA perspective also. A few lectures down the line, and there you will also see this again. But then for now, we know that a merge sort gets executed with two subproblems of n by 2 plus a work done at, let's say, a constant amount of time, which is Cn, right? Here C is 5, n is n, right? So anyway, we will cover this recurrence relation. The formation of the recurrence relation is not in the scope of this particular lecture. We are assuming merge sort has a time complexity like this, or a recurrence relation like this. Similarly, quicksort will be having some recurrence relation like this, right? And that also we will cover in some subsequent lecture when we start quicksort. And then there is one more which we have not touched upon, and that is called as the transformation recurrence relation. What is happening here is when we talk about transformation, then we are actually talking about something which is decaying much faster than actually a division. So division will decay like this. Division will start from, let's say, if it is 16, it will become 8. Division means what? Division means, let's say, tn by 2. So each subproblem is getting broken down by 2. So if that is happening, then the first subproblem is 16. Let us say this is my n, right? The second subproblem will be 8. The third subproblem will be 4. Then it will be 2. Then it will be 1. This is my base condition. I will stop. How many times did I divide? I divided this 4 times to get to 1. Now let us say that I do t root over of n as my subproblem. Then I start with the same 16, which is my n, and then if I start with that, the next time it gets to root over of n, which is 4, and this becomes then this 4 then next time will be reduced to 2. This 2 will be reduced to 1, and this will be my base condition, right? While how many times we did? 3 times. Now I took a smaller number 16. You take a larger number 64, you will see an appreciable difference. You take a still larger number 256, you will still see an appreciable difference. So which means that the t root over of n is actually transforming the size of the subproblem drastically, right? It is changing the size of the subproblem drastically. It is reducing the size of the problem drastically as compared to division. That is why, since it is changing drastically, right, we are calling it as a transformation problem. So that's why we call it as a transformation problem, right? So this is what we have in terms of the 3 things that we will discuss. We will discuss a balanced tree, how to solve the recurrence relation using recurrence tree and substitution method. We will see the unbalanced tree, how to solve the recurrence relation using the substitution method and recurrence tree method. And then we will also talk about the transformation recurrence relation. There we will only see recurrence tree method because substitution method will be similar to the other 2 methods, other 2 trees, but typically these kind of problems of t root over n is not done using substitution methods because it's going to be lengthy, and hence an alternate method will be discussed. That will be discussed in the next lecture, which is on Master's theorem, right? So these are the 3 things that we will cover in terms of non-linear reduction recurrence relations. Now if we go to the first preliminary thing that we have to remember, any recurrence relation that we have to find what? The time complexity of n. So our whole goal is to find this in terms of theta, right? So if we want to find out this in terms of theta, then please remember that if in some expression this comes up and then this also comes up with a plus, minus, whatever in between, right? The dominant term will be the time complexity. The rest of the term can be discarded, right? Why it is the dominant? Because this graph is much above this graph, right? So if I say that n log n is my time complexity, it actually takes care of saying theta n or big O of n is also the time complexity, right? We are taking an upper bound, and that is a safe bet, right? So which is why it is always safe to be upper bound then lower bound, and hence if we have an upper bound time complexity, it will be a dominant term, and we can safely say, for example, if this would have been represented as theta of, or you have solved this, let's say we will do a recurrence tree solution, and then if we have solved this as let's say Tn is equal to theta of n log n plus theta of n, then we can from an asymptotic standpoint say that this is equal to theta of n log n. Please remember this concept, that dominant terms of asymptotic complexity class is an upper bound, and hence can overshadow or can be represented only with that upper bound, rather than trying to find a mathematics or algebra between n log n and n, right? There's no need to find a mathematics or algebra between that, because we know these are well-known complexity classes, and the upper bound is a dominant term. We'll write the upper bound. Please remember that, right? So now let's move on to the actual recurrence tree solutions. So if you remember, we had talked about three things: balanced, unbalanced, transform. We'll take each one of them. Let us talk about the balanced tree first, right? So if we talk about the balanced tree first, then this is our problem, and if you remember from the previous lecture, we had said that we would take a level, we would take recursive call, and we are doing the same approach as we have done in linear reduction recurrence tree. And I told you that I'm going to do a generic method in linear reduction. You will not realize the sum of work, why it is that column is required. Here you will now appreciate why that column is required and why I had taken that particular approach there. So this is my work tree part of it, and my next part is going to be the sum of work. Right, so this is what we are trying to do here. Now the levels, let us start doing this. If you remember, we start with I equal to 0. The recursive call at the I equal to 0 is Tn. The work done is 5n, if you see here. So the work done will be 5n. This is a node. Please put it in as a node style, right? And the work, sum of the work here is still 5n, because I have only one node of 5n. So that one node is contributing to the work done of 5n. Now if I then take I equal to 1, then this Tn breaks down into two parts. One part n by 2, another part n by 2, right? So that's where we are going to get T n by 2 as the first part and T n by 2 as the next part, right? So these two are the parts that we will get as a sub problem from this. Now this Tn by 2, when it executes itself, then it will take 5n by 2 amount of work, because if at a Tn position it took 5n amount of work, at a Tn by 2 position it should be doing 5n by 2 amount of work. So I can write that this is 5n by 2 amount of work, and this is 5n by 2 amount of work, right? So this one will be doing 5n by 2 amount of work. This sub problem solution will take 5n by 2 amount of work. So my total work will be what? My total work will be 2 times of 5n by 2, right? So let us keep it at that. And this is definitely equal to 5n, which you can of course make out, but I'm keeping it at that just to create a pattern. 2 times 5n by 2. Now if I take the next step, I equal to 2. If I go to I equal to 2, then I will be reaching where this Tn by 2 will break down to Tn by 4 once and one more time to Tn by 4, because each Tn by 2 will break down 2 times as per this recurrence relation, that is this 2, right? It will break down by whatever is the original value of n by 2. So original value of n was n by 2, it breaks down 2 times, n by 4, n by 4. The other Tn by 2, this one, so this is the breakdown. So this has broken down to these 2, but this will also break down to this 2, right? So I will just omit this. I hope you have understood that. And this will be now therefore Tn by 4, and then this will also be Tn by 4. So now what will happen is, here 5n by 2 will be actually becoming 5n by 4, because we are now inside a node whose subproblem size is n by 4, and for every subproblem size of n, we are supposed to do a subproblem work of 5n. So if the subproblem size is n by 4, we'll do 5n by 4, right? And the easiest way to remember is whatever is here, just write it as a replacement of this n by 2, right? So if it is n by 4 here, put it as 5n by 4. If it is n by 2 here, put it as 5n by 2. If it is n here, put it as 5n. So whatever is that, put it there. That's the thumb rule, but then you can always calculate and do things. So this will be 5n by 4. So my 2 Tn by 4s are taken care of. This is done. This is done. Now this one and this one will also be 5n by 4, and this one will also be 5n by 4. Net what will happen is this this particular subproblem will therefore be 4 multiplied by 5n by 4, right? So this is going to be the size of this particular, or the sum of the work of this particular subproblem. Now what can we infer from here? Can we infer these things? Let's try to infer, let's try to create a pattern. Can we see Tn by 4, Tn by 2, etc.? And at I equal to 2, if it is Tn by 4, then can I say that Tn by 4 can be written as Tn by 2 square? Because this is 2, so I am saying 2 square, right? From this 2, I am saying 2 square. And how many times is these subproblems are there? How many subproblems are there, right? Or how many times Tn by 4 is there? 4 times, which is also written as 2 square times. Why I am putting 2 here? Because this is 2, right? I am trying to create a pattern between I and 2 here, right? So I have put I here, which is 2. I have put I here, which is 2. So I am saying that each subproblem is of size Tn by 2 square, and this Tn by 2 square will occur 2 square amount of times for I equal to 2. So this will also, this subproblem work, rather this is not a subproblem, this is the work, 5n by 4, can I say this is 5n by 2 square, which is actually counted how many times? It is counted 2 square times, right? So how many times does this exist? 5n by 4, it exists 4 times, which is nothing but 2 square times. So I have successfully converted this 2 into 5n by 2 square and 2 square amount of time. This is what you have to do in every recurrence tree. After I equal to 2, find the pattern, right? As we have found it here. So can I find a pattern here also? I can find a pattern here also. Let's see the pattern here. What is the pattern here? This says that this is going to be 2 square 5n by 2 square. Similarly, this will be 2 1 5n by 2 to the power 1, and this will be 2 0 5n by 2 to the power 0, right? So I'm finding a pattern here, same pattern as I have found. So I can therefore now move into I equal to k. Let me write it as I equal to k. So I've moved into I equal to k because I could find a pattern with I equal to 2. So I'm now in a position to say that at I equal to k, I should be getting a subproblem of size t by 2 to the power of k. How many times? How many times? 2 to the power of k times. Right? T by 2, t by or tn by 2 to the power of k should exist 2 to the power of k times. Why? Because at I equal to 2, t by n by 2 to 2 square was the subproblem size. So at I equal to k, tn by 2k will be the subproblem size. Now this subproblem existed 2 square amount of times because I was 2. So this subproblem will exist 2k times because I equal to k. Right? So this is how you will interpret from I equal to 2's pattern to I equal to k. That's the process that you can adopt. Now different styles will be there, different books will talk about different styles. You are free to follow that. I'm just giving you a method that I feel is comfortable, that I feel is very mechanical, that I feel is less thoughtful, right? You can just use mechanics and actually do it if you follow the pattern that I'm saying. Now, if this is the case, then let us now talk about this side, right? We will say that at I equal to k, we definitely will have what? We definitely will have the work done as 5n by 2 to the power of k. This will be the work done. How many number of times? How many number of times this 5n to the power k will appear? So this will appear 2k number of times. Why is that so? Same logic. If I was 2, then 5n by 2 square was written. So if I was k, then 5n by 2k will be written. If I was 2, then 2 to the power 2 times it was there. So if I is k, then 2 to the power k times these numbers will be there. I hope that makes it clear. So when you sum this up, what are you going to get? When you sum this up, you are going to get 2 to the power of k times of 5n by 2 to the power of k. So 2 to the power of k times, if you are actually adding up 5n by 2 to the power of k, it is a multiplication of 2 to the power k into 5n by 2k, right? Which is what? Which is nothing but your 5n. Right? So this is what you get as 5n. So if you see everywhere your output sum of work is 5n only, right? We are anyway creating a pattern so that at the I equal to k and at the I equal to the last value, we are able to decode what is the sum of work. But if you really see, it is 5n everywhere. Every level it is 5n, right? So now let us move to the last level. And in order to move to the last level, we have to rely on what? We have to rely on one important thing. And that important thing is saying that we have T1 equal to 1, right? For all practical purposes, we will say that T1 is equal to theta of 1 rather than directly calling it as 1. So if that is the base condition, then we know that this subproblem division that we are doing here, I hope you understand that here what are we doing? We are actually dividing the subproblem. Every time we are building a tree and slowly going down and dividing n. N is getting divided. N by 2, n by 4, n by 16, etc. etc. So what will happen finally? N will reach 1. And when n reaches 1, this is what will happen. Because this is our n. N has reached 1. Then my output is 1. That means the time taken is constant, right? At T1. So that is my base condition. How do I write that base condition? Can I say that this will become 1? So if I say that at T1 I have theta 1, which implies that this particular n by 2k should be equal to 1, because we are saying that if n by 2k is 1, then at the last level this should be T1. That means n by 2 to the power k should be 1. So can I therefore write that n by 2 to the power k will be equal to 1, which implies n equal to 2 to the power of k, right? Which implies n equal to 2 to the power of k, and this in turn implies what? This in turn implies that k is equal to log base 2 of n. K equal to log base 2 of n. Right? So now I have a value of k where things will stop. So 0, 1, 2, 3, I will increase, go to k, and then k will further increase. And then k will become what? K will become log base 2 of n, and it will stop. And that's what we calculated. We assumed that it will become 1, and from that 1, we calculated the value of k, saying that k, I will increase from 0, 1, 2, 3, 4 to k, and then finally k will also increase. And then when k reaches to log base 2 of n, things will stop because it has reached t1. So can I therefore say that my last iteration will be at I is equal to, what is my value of k that we have found out? Log base 2 of n. So my last iteration will be here. If my last iteration is here, then what is the value of the recursive call? T1, right? Because n by 2 to the power k will be becoming 1. So think from here, right? The method is to think from this line. From this line, you are trying to create this line. So see, I equal to k, and what is k? K is log base 2 of n. So I put log base 2 of n here in place of k. This is n by 2 to the power k. N by 2 to the power k we had assumed as 1. So I put t1 here. So what am I doing? I'm just replacing the value of k from the I equal to k equation to create my last row where things will stop. Right? So this is my t1. And then what is going to happen is this t1 will execute itself how many number of times? 2k number of times, right? I told you take the help from here, 2k number of times. So if it executes itself 2k number of times, then what is 2k? 2k is n. So then t1 should execute 2k number of times, which means n times. T1 will execute n times. So can I therefore say that this 5n will actually become theta of 1, because at t1 the work done is theta 1. We have already established it here. T1 is theta 1. So at t1 we are going to do theta 1 work. How many times? We were doing it at k 2k times, and 2k is equal to n. So definitely this will be n times, because 2k is n. I told you, right? Take the help from the previous kth stage. Take the help always from here to do every column here, right? And that is the process. So now once you do that, can you therefore say that this becomes n multiplied by, the work is n multiplied by theta 1, right? So the work is n multiplied by theta 1. Now this completes our recurrence tree. Now we have to calculate the amount of work that has been done. That is the sum of all of this. Sum of all of this will give me my amount of work done, and that will be my time complexity. That is our job. How to do that? The way to do that, we had done it in the linear reduction, same process. From I equal to 0, this is I equal to 0, to I equal to n minus 1, and this is not n minus 1, we will do it as n minus 1. From I equal to 0 to I equal to n minus 1. N minus 1 is what? Log of n minus 1. Because the last stage, if I say, is I equal to log base 2 of n, the previous stage is log base 2 of n minus 1. 5n, 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 5n will exist till what time? Till the last time? No, the last time is n, not 5n. But just before the last time, it would be still 5n. And just before the last time means I equal to log base 2 of n minus 1. So can I say that therefore my work will actually go, I'm just writing it at the top, my work will be actually a summation of I equal to 0 to log base 2 of n minus 1. Just before this stage, there still will be one more 5n, right? So that's what I'm trying to write here. So that will be 5n plus this last amount of work. So what I'm saying is this entire work, right, plus the n theta 1 will be the total amount of work that you need to be worried about. So this plus n theta 1 will be my total amount of Tn. right? Let me quickly write that in the next slide so that I don't forget it. So we have actually done as Tn is equal to sigma of I equal to 0 to log base 2 of n minus 1 for 5n and for theta 1 outside the sigma. So this is my work from the 0 to n minus 1 levels, and this is my nth level work, right? So that is what we have written here as far as the individual work aggregation of all the levels of the recurrence tree is concerned. This is how we do it. Now once you have this, we have to solve this sigma. That's the process. So solving sigma is fine. See, it's very simple. 5n, you are doing a summation from 0 to n log n minus 1. What do you think 0 to n minus 1 is? 0 to n minus 1 is nothing but n number of times, right? 0 to n minus 1. I didn't say 0 to n. If I said 0 to n, it would have been n plus 1 times. I said 0 to n minus 1 times. That is n times. So then can I say that 0 to log n minus 1 times is nothing but log n times? I can definitely say that, right? So then can I say that 5n will be summed up log n times, right? So I can definitely say that log base 2 of n multiplied by 5n plus theta 1 will be my output. In fact, I think I did a mistake here. It should be n theta 1. Yeah. So if you remember here, we had taken n theta 1 because this was n theta 1, right? So I just a copy paste mistake. Apologies for that. So this should be this should be n theta 1. This will be n theta 1, and therefore this becomes now what I told you. Remember the asymptotic graphs. The graph of log base 2 of n into 5n is nothing but, remove the constants, so it becomes n log base 2 of n plus n theta 1, and n theta 1 is not dominant, n log base 2 of n is dominant, therefore write Tn as n log base 2 of n, and that becomes the solution for this particular recurrence relation. You have successfully found out the complexity of that recurrence relation, right? A recursive equation was solved to find out the complexity. So that's how we have approached this problem. Just summarizing what we discussed, we have taken the recurrence tree method to solve a recurrence relation. We have shown the recurrence relation. Then we have created the columns. Then we said we'll move from I till the last stage. Last stage is no more 1. It was 1 in reduction, linear reduction. I0, then I1, I2, etc., etc. And then finally it went to whatever value of I we could go to. In fact, in the linear reduction, we went till n, right? I0, 1, 2, 3, 4 to n. Here we are going from I0, 1, 2, 3, 4. We cannot go to n because it does not go, or it does not divide n times. Division can never happen n times. If reduction happens n times, then division can never happen n times. Much before it will stop, because it will reach 1. And that's why, where will it stop? It will stop at log base 2 of n. And we have established that log base 2 of n. I hope you understand how we have done this. Always remember that move to the second level, right? From the second level, create this. This is your generic form creation starting, right? So you are creating this generic form, starting part of the generic form. Then create the generic form, which is your I equal to k. And then use every value of I equal to k to create your last level. Last level, you'll have to use the base condition, right? So this is the same process we have done in linear reduction. Please watch that video also, plus this video. I'm sure it will be clear. Then the process is easy. Just sum up everything here till the penultimate level, because the last level is different. Every level before that is this. So sum this plus this, right? So that's what we have done here. Okay, so that's on this particular problem. Now let's use the substitution method in order to solve this problem. We have done the recurrence tree method. We'll do the substitution method. So our problem statement is this. Let me write this here. Our problem statement. 1 minute, I'm changing the pen. Yeah. So our problem statement is this. Fine. This is our problem statement. So our first substitution, again I'm following the same approach as I had done in the linear reduction approach. Our first substitution is the recurrence relation itself. So it will be 2n by 2 plus 5n. This will be the first substitution. Right? I hope you know what is substitution method. Otherwise, please watch the linear reduction recurrence relation. We are going to actually substitute the lower subproblem solutions to the higher subproblem so that we can actually get to the outcome. Right? I hope you remember I told you that if this subproblem is breaking into these two, that means if you solve these two, you can actually solve this. That's what we are doing. We are trying to solve this and substitute this into the higher subproblem in order to get to a solution. That's what substitution method is. Now, this is the first substitution. Now, let us talk about the second substitution. Right? In the second substitution, our starting point is always the previous substitution's output, which is this. Right? Now, we need to know, if you have to solve this, we need to know this. So let us find that. So we will find Tn by 2. Where will we put Tn by 2? Here, in the main problem. Right? So we will put n as n by 2 here. Then what do we get? We will get 2t n by 4 plus 5n by 2. That's what we will get. Right? So this is what we will get as that particular problem. Now, if we have found Tn by 2, then can we put whatever we found here so that we can now get to Tn? So can I therefore write that my Tn is going to be 2 times 2t n by 4 plus 5n by 2 plus 5n. I just substituted this into the this particular equation. Then let us solve this. Let us say that if we simplify this further, this becomes 4tn by 4 plus 10 n by 2 plus 5n, which is equal to my 4 t n by 4 plus, I can say, see, this will 10n by 2 is what? 5n. 5n plus 5n is what? 2 into 5n. Right? 2 into 5n. So I'll keep it at that. I'll not break this down further because, as you know, in the last lecture also I had discussed that we will try to adapt to a situation where I'm trying to work out a way to create patterns. Right? I will not let simplify things further till I actually find out a way to get to a pattern. In substitution method, we will have to go to the third substitution, unlike our recurrence tree where we used to go to the kth iteration after the second iteration. Right? Here we have to go to the third substitution just to establish the pattern properly. So as I said, okay, so this is your output from the second substitution, and I'm going to use the output of the second substitution as my input to the third substitution. So I will write this down here again, 4t n by 4 plus 2 into 5n. This is what I will write. Now I need to solve this, which means I need this. So we need Tn by 4. So let us solve Tn by 4. So we will say Tn by 4. Where do I put this Tn by 4? Again in the main equation. Right? So we will get what? So we will get 2t n by 8 plus 5n by 4. Now we have got Tn by 4. So if we have got Tn by 4, we can substitute it here back in order to get our Tn. So then Tn will becoming equal to 4 times of 2t n by 8 plus 5n by 4. And Tn already had 2 into 5n, so we'll have to add that. That is 2 into 5n. Right? And that means that we get our Tn as, can I say this is what? Okay, let's write it down like this. So this is 8t n by 8 plus 4 5s are 20. See, 4 5s are 20. And this, in fact, 4 into 5, this 4 will cancel out. So it is still 5n plus 2 into 5n, which means it is 3 into 5n. 3 into 5n. Right? So it is 3 into 5n. Can I therefore write this? Now see, I want to include this 3. Now I have done with first sub, second sub, third sub. I should be finding a pattern now. So 3 has to be my keyword. I have to find a way by which I can utilize this 3 in my output. 8, how is 8 related to 3? 2 to the power 3. T, n, again 8, 2 to the power 3. Plus 3 is anyway there, 3 into 5n. So this is what will be your third substitution. So this is your output of the third substitution. Right? So now that you have found till third substitution, now we are in a position to probably go to the kth substitution. Right? So if we just write what is our third substitution, just so that we remember from the previous page, we had found out that our third substitution is Tn equal to 2 cube T n by 2 cube plus 3 5n. And then we had found out that the kth substitution, or rather we will find out the kth substitution is going to start from here. And can I therefore say if this is 3, this is 3, this is 3, this is 3, I can definitely say Tn is equal to 2kt n by 2 to the power of k plus k into 5n. Right? And this now can be put with the base condition. So I know my base condition is T1 is equal to theta of 1, which means at the end, if k grows, at some point k will get to such a situation that this will become T1 and stop. If this becomes T1, then I hope you can understand that n by 2 to the power k will be equal to 1, which implies in the previous recurrence tree you would have seen that n by 2 to the power k equal to 1 implies that n equal to 2 to the power of k, and then which also implies that log base 2 of n is equal to k. And therefore if we now solve this, we can therefore write Tn is equal to, for k we will substitute what? Log base 2 of n, because k is log base 2 of n. So 2 to the power of k will become 2 to the power of log base 2 of n. Right? And then T1 is T1, and then k again is log base 2 of n, and then 5n is 5n. So I removed I removed k, and everything came in terms of n. That is our job to do after the kth substitution. Find out Tn in terms of n. Now 2 to the power log base 2 of n is n. As per the logarithmic property, you will know that 2 to the power of log base 2 of n is n, because we are at base 2, our base is also 2, our log's base is also 2, so n comes out, right? So that is n, and then T1 is actually theta 1 plus log base 2 of n into 5n, right? So this is n theta 1 plus, removing the constants, we have n log base 2 of n, Now which is the dominant term? This is the dominant term. Same equation we found in recurrence tree, same equation you will find in substitution method. So either method you do, you will get to the same equation. So this Tn therefore becomes the dominant term, which is n log base 2 of n, and that is your answer. That becomes your answer. So this is how you will do the substitution method given a recurrence relation. We had done this for the linear reduction, but in the linear reduction it was very easy because it was just reducing by 1. Here you actually get into the usage of recurrence tree substitution method because you are doing divisions, right? And with divisions you need these tools to actually solve it, and that's what we are doing here. So now let's get into the next style of divide and conquer, which is the unbalanced divide and conquer. And let us take an example, and we had already discussed this earlier, that the example will be towards the divide and conquer using the quicksort method, and that quicksort method will say that there will be disparate work sizes of the subproblems. So one subproblem will be Tn by 4, another subproblem could be Tn by 2, they are not same in size. The work done at each level is the same, theta n square, which is okay. And this is my base condition. So now if we move with this concept, we'll do the same thing. We will start doing it in the same manner, which is we will start solving the recursive tree method for this particular problem. Now this is going to be a bit tricky, so be with me. At some point we will try to make this a very simple problem. Let's see if we can do that. So we have a level. We have recursive calls, then we have the work or the tree, and we will also have the summation of the work, the same set of columns that we had taken earlier. Now if I take the first I, which is I equal to 0, my recursive call will be Tn. Same thing, my work is n square because this is what is the work. So my work is n square, and the summation of the work, because this is the only work being done, is n square at this level, right? So now if we move on to the I equal to 1, then this breaks down into two subproblems. One subproblem is Tn by 4, and this occurs one time because the equation says 1 Tn by 4, so I will take 1 times Tn by 4, and then it also has broken down into Tn by 2, which occurs one time because the equation says 1 Tn by 2. So these two together will become the position of I, the ith iteration. So the equation here, the work done for n by 4 should be, if the work done for n is n square, then the work done for n by 4 should be n by 4 whole square, right? Simple as that. Then this work will be n by 2 whole square. As I said, you can put n by 4 in the previous n and calculate what it happens, or just take this n by 4, n by 2 and just replace this n, whatever way you choose, right? The summation of this is going to be, let us say, I'll break this down. So it is n by 16 plus n square by 4, which is n square plus 4n square by 16, which is 5n square by 16. This is what will be the work summation for this particular I. We'll move into the next value of I equal to 2. Now n by 4 can actually go to two ways. I mean n by 4 can break down by in two ways. N by 4 can break down with one of the ways is n by 4 to n by 8, because this n by 4, see, if this is n by 4, then this is n by 4 of, I mean n by 16 of that, right? So n by 4, if this is n by 4, then I will have to divide n by 4 by 4 times to get to this, and I'll have to divide n by 4 2 times to get to this. So this n by 4 can divide itself into two parts. One, it can divide itself into Tn by, first time n by 4 gets divided by n by 4, that is n by 4 by 4, right? N by 4 is the substitution to n, then n by 4 has to be divided by 4, because if it is n, you divide by n by 4. If it is n by 4, then you divide by n by 4 will be divided by 4. So we will actually be having n by 16. So n by 4 will divide into n by 16, and this will happen one time, and we will also have Tn by see, if it is n by 4, then you have to divide it by 2 again, so Tn by 8, right? So that will be one time. Are we done? No, because we just completed n by 4, so we have to also complete n by 2, right? So if it is n by 2, this becomes n by 8, so we have Tn by 8 one time. Notice that Tn by 8 is coming 2 times now, right? And therefore we now can have Tn by n by 4. What was this? This was our Tn by 2. Tn by 2 became Tn by 4. Tn by 2 will become Tn by 2 became Tn by 8, and Tn by 2 will also become Tn by 4. So this will be Tn by 4 one time. How will our nodes look? Let us see how our nodes will look. So here what we will get is, as I said, take this n by 16, substitute in place of n. So we have n by 16 whole square, and then put a node around it. Then we have n by 8 whole square, and then put a node around it. Then we have n by 8 whole square, put a node around it. Then we have n by 4 whole square and put a node around it. And when you do this, you can now calculate what is going to be your work done. It's going to be n by 256 plus 2n square by 64. Why? Because there are two n by 8s, right? So I said 2n square by 64 plus n square by 16, which is equal to n square plus n square plus 1 minute, just 1 minute. Yeah. So this is going to be my n square. Let's see the LCM first. The LCM is going to be 256. So this will be n square. 64 will go 4 times, right? So 4 2s are 8. 8n square plus 16 n square, which is going to be 25 by 256 n square, which is again can I write this as let's hold on to that. We will write that, but not now, right? I will write that. We have to come to a generic solution for this because we have reached I. So let us now start writing the generic solution. Before that, let us figure out a way to probably solve this problem. This problem is not the run-of-the-mill problem because it is an imbalanced node breaking up, and therefore you cannot have the generic method to solve this problem. What we need to understand here is, and we will come to this, I have kept an equal to here, placeholder here, I'll come here. What we have written here is that if this is how I equal to 2 behaves, that means that starting from n, you can actually divide it to n by 4. This n by 4 can be divided to n by 16 and to n by 8. Right? Or this n by 4 could have been divided into n by 8 and n by 4. Right? It can go to either ways. That means if I start from a particular node, how many ways can I divide a particular n? Let us try to establish that. See, what we'll write is that if I equal to 3, then how many divisions are possible? Let's try to figure out the divisions possible at I equal to 3. And please try to understand this part a bit carefully. So, if there is first time this n can divide by 2. See, n can be divided by 2 or n can be divided by 4. So can I say that the first time n can divide by 2? Right? Can I say n can be divided by 2? Of course I can say that. So let me write this a bit here so that I get some space. Okay. So divisions possible. Divisions possible is the first time I can divide this n by 2. So I got my Tn by 2. Now this Tn by 2 can be divided further by Tn by 8, or it can be divided by Tn by 4. That means here what I have done, I have divided this Tn by 2 by another 2. Right? So this Tn by 2 got divided by another 2. So the possibility is that I will divide it again in the next level by 2. So I get Tn by 4 because this is the division. So this in the next level can again be divided by 4, which means I could get Tn by 16, or I could divide it by 2 and I get Tn by 8. How did I get Tn by 8? By dividing this by 2. So the same thing which was divided by 2 was again divided by 2. So I started with Tn and I did one division by 2, one more division by 2, one more division by 2, and I reached to I3. I hope you understand that concept. So this is one path in which you can have a subproblem. I have to find out how many ways in which a subproblem can exist at I equal to 3 and then try to figure out the genetic pattern. So you can very well understand that you can either divide a particular layer by 2 or you can divide that layer by 4. So there are only two possibilities to do. Right? There are only two possibilities to do, and we are talking I equal to 3 and two possibilities at each stage. So here it could have been 4 also. Here also it could have been 4. Here also it could have been 4. So how many such combinations we will have? You have done it in your Boolean algebra days, right? 0, 1 you have done, right? A state can have 0 and 1. Here we are saying a state can be 2 and 4. So we can divide by 2 or we can divide by 4. That's the only things we can do. And how many times we can do it? For I equal to 3, right? So these 3 should be there. How many combinations of these 3 is possible? So what we had learned earlier was that we will put 2, 2, 2. The number of ways possible, of course, you will remember that because we have 2 states and then we have 3, I equal to 3. For that we will actually put 2 to the power 3 equal to 8. So we need 8 more combinations. What are those combinations? 2, 2, 2, 2, 4, 4, 4, 4. Right? 2, 2, 2, 2, 4, 4, 4, 4. These are the combinations. And then this next time we will do 2, 2, 4, 4, 2, 2, 4, 4. Then we will do 2, 4, 2, 4, 2, 4, 2, 4. So these are the ways in which you can actually break down a problem at the third level. At the third level, you could have everything divided by 2 at every previous levels. You could have the first and the second as division by 2 and I equal to 3 as division by 4. So these are the ways in which you can break the problem. I hope you are understanding. So let we have j number of times, let us take j times it is divisible by 2. Let's say j times we divide by 2. Then at one particular combination, if we divide by 2 by j times, then we can therefore divide the other possibilities by I minus j times, right? Divide by 4 how many times? So this is division by 2. Then division by 4 is how many times? Division by 4 we can do I minus j times, because I is my total number of times, 3 times. See, we get divided by 3 times, 3 times, 3 times, 3 times. So if 2 is taking 2 is taking j, I mean division by 2 is done j times, then whatever is left will be I minus j times. It cannot be more than I, right? We have to get to 3. So I minus j times only. So see here, if 2 was dividing 2 times, then I can only do division by 4 1 times. Why? Because I is 3. 2 has already taken 2 times. So I can do only 1 time. So therefore, I minus j times, I will say division by 4. Right? I minus j times division by 4. So my final size, therefore, will be that every time I will take n divided by 2 to the power of j and 4 to the power of I minus j. Right? Every time I am dividing n by 2 to the power of j and 4 to the power of I minus j. So this becomes my subproblem size. Right? So we were unable to find the subproblem size because we had so many variations. This was one subproblem, this was one subproblem, this was one subproblem, this was one subproblem. How do we find that subproblem size? Because it's no more uniform, right? We cannot find the subproblem size like this in the standard way. So we will have to resort to this particular way in which we find out the combinations of these subproblems and then we find the final size of the subproblem. So this is my final subproblem size. I hope you understand this till this part. Be with me. You will slowly get there. So therefore, at I equal to k, now it's time to probably talk about this. This is actually 5 by 16 whole square n square. Right? So can I say that I told you, right, after you reach I equal to 2, try to find out the pattern. We found out the left hand side, we have found out the pattern here. We have to find out the pattern of this also. Right, so let us say what are the patterns here. The pattern here says that it should be, can I say that, see, this 2 is there and I have used this 2 here. This 1 is here, this 1 is here, and I have used this 1 here. So can I say this is 5 by 16 to the power of 1 n square? Can I say this is 5 by 16 to the power of 0 n square? So you are getting a pattern. You are getting a pattern for the sum of work, and that's all you need. You don't need to really know, like for example, come down here, come here. Here what we had done is we understood that this was our subproblem pattern, right? But in order to understand this pattern, we had to find out 5n by 2k how many times. Similarly, we had to find out at I equal to k what will be the subproblem size, how many times the subproblem size will be there. See, this is your subproblem size, and this is how many times the subproblem size will be there. This is your work, how many times the work will be there. That gives you this pattern. But in our case, and remember what we did, once we are done with this, I don't need this part. I just need this part in order to calculate my time complexity. So should I waste my time finding out all of this when I can't find out? If I would have found out this independently, I don't need to find out this at all. I can bypass this because this is all I need. Right? And that's exactly what we'll do in this subproblem. Right? So let's go back here. And let us see where we are. So we are saying that we know this. If we know this at I equal to k, would we know what is this? Of course we will know. Right? So all we need to know is this side of the problem. Do we really care about this side? We don't. Right? Still, let us see how best we can represent it from an exam standpoint. Right? So what we'll do is, we will say, therefore, so let us go to the I equal to k. Okay, so let me put level, let me put recursive call, then let me put work tree, then let me put sum of work. Okay, now we are talking I equal to k. So for I equal to k, at I equal to k, at I equal to k, can I say, come back here, what had we written? We had written this, remember this, that the problem size is n by 2 to the power j 4i minus j, right? This was the problem size. So the recursive call at I equal to k should be t, sorry for this, 1 minute, let me change the color, yeah, t of n by 2 to the power of j 4 to the power of k minus j, right? I just took the earlier derivation that we had done, that the problem will be breaking down into n by 2 to the power of j. That means by 2 I can do j times, then by 4 I can do k minus j times, because I equal to k, I cannot cross k, right? So my recursive call subproblem size, this is my size, and this size will be how many times? This size will be how many times? I don't know how many times, and I don't care. I told you, right? In various combinations I'll write, in various combinations. I don't know how many combinations it could be. I don't know what are those combinations, and I don't care, because all I need is my right hand side work. But I can still write this, that my subproblem size will be this, and depending on the value of j, the subproblem combinations will be different, right? So that is why I'm saying in various combinations. And my work done at the node will be n by 2 to the power of j 4 to the power of k minus j, and this is whole square, and this is my node, and this node will be how many times? I don't know and I don't care. Again the same thing, I don't know and I don't care. So this will also be in various combinations, right? So this will also be in various combinations, but definitely this is something that I know, and this is the most important thing I do care, which is 5 by 16 of k n square. If you go back here, you will understand what I'm saying. It was 5 by 16 square n square for I equal to 2. Then for I equal to k, it will be 5 by 16 k n square, right? So that is what I care. I could find out the amount of work. So if I actually add this, that many number of times of the combinations, I will get this. So why do I care about this? I already know this. This is what I needed at the end, right? So I don't know, I don't need this. I don't need this. That's all, right? So then what we will say, therefore, is that from here, I will say, yeah. Okay, let me see how much space I have left, because we have to go to the substitution method also. So the substitution method, I have kept 2 slides, so I have to finish off it in this slide, which doesn't sound that it will be possible. Okay, fair enough. So let's finish off this slide, then I'll create a placeholder. So what we'll do is that we have established for I equal to k. Now I explained to you that when a node divides by 4, let's say this is the division by 4 and these are the divisions by 2 and this by 2 again gets divided by 4 and then it again gets divided by 2. So this is by 2. Then the by 4 will hit 1 much faster. By 4 will become 1 much faster than my by 2. So this will go till 1 after traversing some levels. Right? So this is what will happen. It will go till 1 after traversing some levels because it is n by 2. So I cannot say at what stage my I will end. That is, k is, I is increasing. I has become from 0, 1, 2, 3, 4, k. When will I end? I don't know, because here I will end much faster. Here I will end much slower. Right? I will end much faster. I will take more eyes to end here. So because of that, we need to find the deepest path, and the deepest path will be when it is getting divided by the smallest number. Right? In our case, it is 2. Right? So the slowest reduction is 2. So the deepest path is what we'll have to find out. That is what is the maximum value of what I can be. Right? That is the maximum value where I will reach the base condition. Right? Which is the division by 2. Right? So division by 2 will be my maximum value where I will reach the base condition. So can I therefore say that my deepest path to reach the leaf is when divided by 2. When divided by 2 continuously, starting from I equal to 0, if I keep on dividing by 2, then when it will reach 1 is the deepest path. Right? So that is what is it. And when is that happening? That is happening at j equal to k. Right? So j will be equal to k when that happens. Why? Because if you see that if I make j equal to k here, then the division by 4 ceases to exist, because 4 to the power of k minus j is becoming 0. Right? I said the deepest path is division by 2. Therefore, division by 4 should not exist. That means 4 to the power of k minus j should not exist. 4 to the power of k minus j should not exist. When will that happen? 4 should not exist. When will that happen? When k minus j is equal to 0, which means k equal to j. And that's what I have written here. Right? I hope this part you understood. So this is when the k minus j will become 0. Right? Now, for I equal to k, therefore for I equal to k, my work problem size will become n by 2 to the power of 2k minus k. Why is that so? For I equal to k, n by 2 to the power of k minus k, because at I equal to k, it is n by 2 to the power of j, 4k minus k. Now, if I equal to k, right, if I equal to k, can I substitute this value 2 to the power of j and in fact k is here, which is 4 to the power of k minus j. Now what I will do is, let me break this down, then probably it will be clearer for you. I think let me not jump a step here. Let me break it down. So I have n by 2 to the power of j, and I have 4k minus j as my work problem size. Can I write this as n by 2 to the power of j, and then 4 I'll write this as 2 to the power of 2k minus 2 to the power of j. So can I therefore write this as 2 to the power of 2k minus 1? Sorry, 2 to the power of 2k minus j. Yeah, 2 to the power of 2k minus j, right? Because this is an index here, 2 to the power j, and 2 to the power of j is here. So 2 to the power j, 2 to the minus 2 to the power j will be added. So there is a minus sign. So there will be a minus sign at the end of the day. So n by 2 to the power of k minus j. So that is what I had written earlier. Now, what and did we say that k equal to j? If you see here, we had said k will be equal to j. So can I put k equal to j here? If I put k equal to j here, this will become n by 2 to the power 2j minus j. Right? N by 2 to the power 2j minus j, or k equal to j. Let me put it the other way around, because we are trying to find out for k. Let's not eliminate k here. Right? You can do other way also, but let's do it this way. So we'll say that this is 2 to the power of 2k minus k. Why? Because k equal to j. So I've substituted j as k. So which is n by 2 to the power of k. This is when your subproblem will be at the deepest depth. Right? Again, let me repeat. We said division by 2 will be the deepest depth, of course. Right? And when that happens, we have to make this component as 0, which means k equal to j. So taking this as the subproblem size, then this, just solving it, we will get this. Putting this value of k equal to j, we get this, and our subproblem size becomes n by 2 to the power of k at the deepest depth. And at that deepest depth, I know we have reached what? Theta equal to 1, because we have been given theta equal to 1 here at that deepest depth. Right? So now we know that my slowest subproblem, my slowest subproblem size is t n by 2 to the power of k. This is my slowest subproblem size. At t equal to 1, then we have theta 1, which implies n by 2 to the power of k is equal to I log base 2, n by 2 to the power of k is equal to, 1 minute, n by 2 to the power of k should be equal to 1, because my theta is 1, right? So this will become t1, which means this entire component will become 1, right? So n by 2 to the power of k will become 1. So when n by 2 to the power of k becomes 1, then n becomes equal to 2 to the power of k. Again, we get the same thing. We get what? We get that k is equal to log base 2 of n, taking log on both sides. So our last iteration will be what? Our last iteration we had done till I equal to k. So at I equal to log base 2 of n, that will be our last iteration. At that last iteration, what is our t? We said slowest subproblem is t n by 2k. At the last iteration, it will be t1. So this will be my t1, and this will approximately be there n times. Why? I'll just explain. So it will be t1 n times, and the problem work will be theta 1. This will also be n times. So my work will be n theta 1, right? The sum of work will be n theta 1. So this is my table where the last row we are writing, right? So all we need to know, I hope you have understood that this is my slowest subproblem size, and that can become 1 at the last iteration, right? It will become 1. So that will become 1 when I is equal to log base 2 of n. Now let us figure out why t1 I am saying n times. See, it's simple to understand. I am saying that the tree keeps branching. The tree keeps branching 2 choices. Every time it is branching 2 choices. Right? Therefore, and I have also established that my max depth is log base 2 of n. So the total paths possible. So the total paths possible is 2 log base 2 of n. 2 to the power of log base 2 of n. Right? Because why? Because I have 2 choices and log base 2 of n as the depth. Then 2 to the power that will be my total choices. Right? Log base 2 of n as my depth. 2 to the power of, just now you saw at I equal to 3. How many choices did you have? 2 to the power of 3. Right? You had 8 choices at I equal to 3. Similarly, at I equal to log base 2 of n, you will have 2 to the power log base 2 of n. And 2 to the power of log base 2 of n is nothing but n. Right? So this is your n leaves. That will be the total number of leaves at the last level. Right? This is why I am saying that T1 will be n times, theta 1 will be n times. So this is why we are calling these as leaves. So I hope this part you have understood. Now we have to solve the summation problem. And to solve the summation problem, let us see how we can move on with that. So what we have here is we will again, it will be 0 to log base. See, this is log base 2 of n log base 2 of n. This is log base 2 of n. That means previous level is what? Log base 2 of n minus 1. Till the previous level, what is the sum of work you will get? This sum of work, right? This will be your genetic sum of work. This is the sigma you will have to put. And at the last level, you get n theta. Right? So the last level will be n theta and then summation of this from 0 to log base 2 of n minus 1. Same as in the previous problem. So can I therefore write that my Tn is equal to sigma I equal to 0 to log base 2 of n minus 1, right? Because till the last level is different. Before the last level, it will be what? It will be 5 by 16 to the power of I n square, right? We know that. Why? Because here we have seen that, right? 5 by 16 k to the power of n square at I equal to k, right? Then the last level is what? Log base 2 of n minus 1. So 0 to log base 2 of n minus 1 times. What will I have to do? I'll have to sum up 5 by 16 k n square, right? So that's the formula. So 0 to log base 2 of n minus times, I have to sum up 5 by 16 I n square. Because I've taken the variable I, I've put I here, right? And this plus n theta. Theta was already there, n theta 1. Theta was already there, n times I showed you, y n times came. Now I can move n outside. So I can say n square sigma of I equal to 0 to log base 2 of n minus 1, 5 by 16 to the power of I. Now this part is what? This part is a GP. So this part is just geometric progression, right? So let us find out the formula for the geometric progression. Let us say that can we write this geometric progression sum as SGP is equal to 1 plus 5 by 16 plus 5 by 16 square plus dot dot dot, right? So why? Because I equal to 0 means this will be 0, so the entire thing will become 1. I equal to 1 means this will be 5 by 16. I equal to 2 means this will be 5 by 16 square, and so on and so forth. So this will go on. What is R here in terms of geometric progression? R is 5 by 16. That is the ratio in which it's increased every time. And what is, let us also take, instead of saying log base 2 of n minus 1, let us take it as m, which is the last number of the geometric series, or the last term count of the geometric series. M is equal to log base 2 of n minus 1. Therefore, we can write that sigma of I equal to 0 to m for r to the power of I is equal to 1 minus r to the power of m plus 1 by 1 minus r. This is your GP summation formula. Nothing new. This is a GP summation formula. So this GP summation formula you have to remember. Remember that whatever you are going to put as r, if that is a fraction, then the formula is 1 minus r to the power of m minus 1, because this is less than 1. Therefore 1 minus r to the power n minus 1 is what you have to take. If this was more than 1, you will take r to the power m plus 1 minus 1, and that's what we will see in the next example. But for now, why I have taken 1 minus r is what I explained, because r is less than 1. So this becomes equal to 1 minus 5 by 16 to the power of log n by 1 minus 5 by 16, which is equal to 1 minus 5 by 16 to the power of log n by 11 by 16. Now 5 by 16 to the power of log n will decay very fast, will become very fast 0, right? Because of the exponent nature of log n. 5 by 16 itself is very small, and log n being exponential, we will try to make it smaller as we go forward, and hence this will decay very fast. Therefore what will happen is the 5 by 16 portion will be equal to 0, and therefore my SGP, the summation, will be left with 16 by 11, because this will become 0, this portion will become 0, this portion will become 0, and therefore we will be left with 11 by 16 in the denominator, which becomes 16 by 11 when we push it to the top. And therefore our Tn will be what? Our Tn was this n square, remember, because we had classified this as the sum of GP, this portion as the sum of GP. N square is still there, so n square multiplied by 16 by 11, and don't forget we also had n theta 1, right? So n theta 1 will also be there. So this so this will be n theta 1, and here also we have a n theta 1 addition, right? So we have an addition of n theta 1, which I missed out here. So this is our total Tn, n square 16 by 11 plus n theta 1. And then this can be therefore written as n square 16 by 11, which is your dominant complexity class, n square. So this becomes Tn is theta of n square, and that is your final answer. So for the problem that was given, which is the unbalanced problem, this is going to be the solution, theta of n square, right? So this shows you how complicated the solution to this can be, and when we move into Master's theorem, you will understand how we can solve this in a much better way rather than doing so much of mathematics. So this is your divide and conquer for an unbalanced problem. This problem has come in your semester examinations, and depending on whether they say Master's theorem or not, if not Master's theorem, that's why I made sure that you know how to do it using a recurrence tree method. I will now also make sure that you know how to do it using substitution method. Substitution method for the same problem will look like this. For the same unbalanced problem, let us attempt to do the substitution method now. So substitution 1 will be the same problem. We will write the same problem again. That's our substitution 1. We'll mark it. Our substitution 2 will start with substitution 1. So we will write the substitution 1 again. The output of substitution 1, by the way, we had to put Tn equal to, so we will say Tn equal to Tn by 4 plus Tn by 2 plus theta n square. This is our starting point. This is also Tn equal to and in order to solve this Tn, we need this and we need this, right? We need both of them. So let us solve one by one each of them, right? So let us solve one by one each of them would mean 1 minute, I'm just trying to change my pen. Yeah, so it will be Tn by 4. I'm trying to solve for Tn by 4, or let's okay, let Tn by 4 is Tn by 8. Where am I putting this? I'm putting this in my main equation. Tn by 4, Tn by 8, then this becomes Tn by 16, and this becomes n by 2, n by 4 whole square, rather n by 4 whole square, right? In fact, I should have eliminated the theta here because we are now into an equation mode. There is no need to put the complexity as theta. We can just write it as n square. So this should have been n square, this should have been n square, and this definitely is n by 4 whole square. Similarly, we have to get to Tn by 2, and that is Tn by 4 plus Tn by 8 plus n by 2 whole square. So we have got these two things now. These are the two things that we needed, and these two things can now be substituted back here, right? So let us substitute them back in their original places so that we get to Tn. So Tn is therefore Tn by 4 I'm just substituting Tn by 2 first. So Tn by 4 plus Tn by 8 plus n by 2 whole square, and then I'll substitute Tn by 4, which is Tn by 8 plus Tn by 16 plus n by 4 whole square. This becomes this substitution and this substitution. We still have n square left, so we'll put n square. Let's simplify this further. This becomes Tn by 4. N by 8 occurs 2 times, so 2Tn by 8. And then we have n by 16. And then we have our work done. Our work done is n by 2 whole square plus n by 4 whole square plus n square, which means it is equal to Tn by 4 plus 2T n by 8 plus Tn by 16 plus, if I take n square common, I will have 1 plus 1 by 4 plus 1 by 16, right? So that is my work done at Tn after substitution 2, right? So can I simplify this further? Yes, one more step I can probably do, which is Tn by 4 plus 2Tn by 8 plus Tn by 16 plus n square into 1 plus 5 by 16. N square into 1 plus 5 by 16. I just took the other part of it and I got to 5 by 16. Why 5 by 16? Because if you remember, our multiplier of the work was 5 by 16. If you remember here, this was the multiplier, right? 5 by 16 to the power of the level that we are in, and then n square was there, and we already have n square outside, and then we have 5 by 16. That is what I'm trying to do here. I already have n square outside, so if I can get 5 by 16, so this is my second substitution. So I'm really trying to say that I have got 1 from the previous layer. If you see here, see this one, What am I trying to say? I am trying to say that I have got 1 n square from the previous layer and 5 by 16 n square from the second layer, right? So just see here what has happened. Same thing has happened. See, I have got 1 from the previous layer and 5 by 16 n square from the current layer. That's my second substitution. So for that, I equal to 1 because I start from 0, 0, 1. So there also I am getting the same thing. Now let's go forward and let's try to see that what is the value going to be at substitution 3. Right, so at substitution 3, can I write here, for lack of space I'm going here. So at substitution 3, can I say Tn is smaller t terms? I don't need to write it as I told you, right? I don't need this, because if I know my work and I've created a pattern, then I can extend that pattern like I'm doing now in order to get to the summation sigma that I would like to do. So 5 by 16 plus 5 by 16 whole square. So this is what it will be, because the next level will be 5 by 16 whole square n square. Why 5 by 16 whole square n square? Just go back here, you will see. The first level was 5 by 16 0 n square, 5 by 16 1 n square, 5 by 16 whole square n square, right? So that is what I have written here also. So 5 by 16 whole square n square. Now you will say that we will be doing it in substitution method. How do we know that? From the previous method, right? The previous method need not be done. Why? Because here itself you are establishing that you are getting to 1 plus 5 by 16, right? And after that you will know that you will get to 5 by 16 whole square after that, because the next substitution that you can easily do the next substitution, because I said do till 3 substitutions. But here, since we have already done the recurrence tree method, I know that this will come as 5 by 16 whole square. The third substitution will come as 5 by 16 whole square. If not, just do it till that third substitution and just simplify it further. I'm sure you will get this part of the problem, which is 1 plus 5 by 16 plus 5 by 16 whole square. Once you get that, the solution becomes easy. That for the substitution of at the kth layer, we will have Tn is equal to sum of all smaller subproblems of size. What is going to be the size? The same thing, we know that it will be n divided by 2 to the power of j and 4 to the power of k minus j. The same way that we have done in recurrence relation. So this is the sum of all the subproblems plus the work done, right? Subproblems of size this, subproblems of size this plus the work done. The work done will be this, sum of I to let's say k minus 1 of 5 by 16 whole to the power of I, right? At the kth layer, this will be what it will be. At the kth layer, Tn will be equal to this plus n square, I equal to 0 to k minus 1. Why is I going from 0 to k minus 1? If you see this, we were at level 3. Here we were at level 3 or substitution 3. And at substitution 3, we are getting square here. So don't you think this will be 1 less than the level? That's why if I put here I, then I should take it till k minus 1, because I'm at k, therefore this will go till k minus 1, right? Because if it goes till k, this would have been 3, but this is 2. So at level 3, if it becomes 2, at level k, it should become k minus 1. I hope you understand that part. Now, we know that, let's say, t theta or t1 is equal to theta 1 when at n by 2 to the power of k is equal to 1. Now this you'll have to do the same way as we have done recurrence relation. So I'm just not repeating the same text. It's the same logic, same text. So t1 equal to theta 1 at n by 2 to the power k equal to 1. So we are trying to establish what? When will tn become t1? When will it end? Right? And for that we have the detailed method that we have done in recurrence tree method. The same method you can use. and n by 2 to the power k is equal to this will mean that k is equal to log base 2 of n. Therefore, our Tn will become what? Tn will become sigma of I equal to 0 to n minus 1 of T1 plus n square of sigma I equal to 0 to log base 2 of n minus 1 5 by 16 to the power of I. What has happened? Okay, what has happened is the smaller problems are going to get done at the last layer at T1, but how many such T1s will be there? We need to know. So that will be I equal to 0 to n minus 1. We discussed that earlier in the recurrence tree problem also, and the same logic you can put, right? That there will be n such levels, each level will have T problems, T1 problems, right? So that way you can say that there will be n times T1 as the number of sub problems that will be there, right? And then this will be the base condition problem, and then this is the same summation. This is the same summation that you do for all the work till n minus 1. Why n minus 1? See here, here it was k minus 1, k is log base 2 of n, so I just substituted that here, and n square is not dependent on I took it out, 5 by 69, right? And then when you solve this, what do you get? You get n theta 1, T1 is theta 1, so this is n times theta 1, right? N times 0 to n minus 1 means n times T1 means n times theta 1 plus n square into the same way sorry about that the same way you will do for this particular log based problem. So the same way that you did for recurrence tree, n square into 16 by 11, the same thing will come, which means that this will be implying that Tn is equal to theta of n square. So net from here there is no difference from the recurrence tree solution, because recurrence tree part is over. After that you are solving sigma in the recurrence tree. Here also you are solving sigma, because at the level k you are defining the problem statement with the sigma, and then you are solving that for T1, right? So that is what you are doing here. This is how you will do the substitution method for the same problem. Okay, now let's get into the transform method, which is the third method of the I won't say divide and conquer, but the non-linear reduction method, right? So let's get into that particular problem that I wanted you to take through this, and we'll do the recursive method for this. And as you can see, we have a problem where the sub-problem size is t root over of n. So as I said, root over of n will be decaying very fast, right? And hence it is called as a transformation. So the entire attribute of the problem will be changing very fast, and hence every stage the problem will be transforming itself. The sub-problem will be transforming itself. And if you find the solution of those sub-problems, you will be able to solve the bigger problem at a much faster pace. So that is what this root over of n tries to signify. So let us try to find out what is going to be the time complexity of this using the recurrence tree method. We'll take the same thing, which is take the levels. This is going to be simpler than the previous problem. It is going to be exactly the same as how we have planned this to be, because there is no unbalance or imbalance in this. Right, so if we have I equal to 0, then I can say that at I equal to 0 I have Tn. My tree node is root over of n. In fact, no, not root over of n. My bad, this should be root over of n. This should be 1 because we have been given theta 1. So this should be actually 1. My sum of work is 1. Now we have I equal to 1. At that I equal to 1, it breaks down into 2 subproblems. Each subproblem of size t root n, t root n. You can write tn to the power of half. Up to you. We will be writing in that style now. But then the subproblem will give rise to work which is going to be 1 and 1. T root n will be doing its subproblem in 1 cost, and another T root n will be doing its subproblem in another 1 cost. So the sum is going to be 2 here. That is what we will keep there. Pattern we will see. As of now, I am not seeing any pattern. So let us go ahead. So I equal to 2. This Tn will first break down into 2 subproblems. So Tn to the half. If we do another Tn to the power half, so this is T root over of n is nothing but T n to the power of half. Now, if we actually say that we will break this again by root over, then this will become T n to the power of half into half, which means this will become T n to the power of 1/4. So when we break T root n by half, then or by root n again, we will get T n to the power of 1/4. This will also be T n to the power of 1/4. That is, from this and this we got this, but we have this also. So for these two we will have T n to the power of 1/4 and one more of T n to the power of 1/4, because we had to make it 2. Right? So this is how we will get 2. And this will break down into 1, 1, 1, 1. Every time T root n is called, 1 cost is needed to solve. So here we will get 4. Now I told you that when we go till I equal to 2 for a recurrence tree, you should start discovering patterns. So see 2 here. How can we make this something related to 2? We can say that this is T n to the power of 1 by 2 to the power of 2. Right? So that is 4. How many times is there? 4 times is there. So this is 2 to the power of 2 times. What about this? This is 1. This is 1. How many times 1 is there? 2 to the power 2 times. 1 is there, 2 to the power 2 times. Right? And then can we simplify this also? Can we generalize this also? Can we say that this is 1 into 2 square, 1 coming from each of these ones, right? So 1 into 2 square. So then I can easily write this as 1 into 2 to the power 1, this as 1 into 2 to the power 0. So I am getting a pattern. Right? So let's go to I equal to k. I am now ready to get into I equal to k. So I equal to k would mean that this will be T n 1 by 2 to the power of k, because for I equal to 2 it is T n 1 by 2 to the power 2, then I equal to k it is T n 1 by 2 to the power of k. How many times? 2 to the power 2 times for I equal to 2, 2 to the power k times then. And this will be 1. How many times this 1 will be there? This will be there 2 to the power k times, because this was 2 to the power 2 times for I equal to 2. So this will be what? 2 to the power of k. 1 multiplied by 2 to the power of k. That's what it will be. 1 multiplied by 2 to the power of k, which is 2 to the power of k. Right? So now uh, it is mentioned here that T1 equal to theta 1. So let us try to feel for that, or let us try to figure out what is going to be our base condition. So this will become T1 at our base condition. So when this becomes T1 at our base condition, then can I say that T2 or T1 rather, T1 is equal to 1. In fact, we have been given this T2 equal to 1, right? I was looking at this, sorry for that, but then we are looking at T2 equal to 1. So let us write T2 equal to 1, which is given. So don't you think that if this becomes T2, it implies that n by 1 by 2 to the power k should be equal to 2. Taking log on both sides, 1 by 2 to the power of k log base 2 of n, because you have n to the power of half k, right? And if you take log, then 1 by 2 to the power of k will come out, any power to n will come out, and then the rest of the thing will become log. That's the formula of log, and or that's the identity, one of the identities of log, and this becomes log base 2 of 2. So this implies that 1 by 2 to the power of k log base 2 of n is equal to 1, because log base 2 of 2 is 1. So 2 to the power k is equal to log base 2 of n, which implies that k is equal to log base 2. In fact, let's take log both sides again. So log of 2 to the power k will be log of 2 to the power n, right? So let me write this. I'm jumping a step unnecessarily. Just be with me. So what we'll say is, taking log on both sides, this is log base 2 2 to the power k log base 2 of n. So log base 2 to the power k is what? It is k, and then the other part remains as such, log base 2 of n. So that's going to be my k. So what am I saying? That the value of k, so k will increase 0, 1, 2, 3, 4, k, then it will further increase till it actually makes or goes till T1, rather T2 in this case. So to stop at T2, I will have to increase beyond k. I is at k, which will go 2k times, but still it has not reached T2. So this has to become T2 for I to stop. What is the value of k for that? We found it as k equal to log base 2 of n. Now, if that's the value, then at the value of that base condition, so let me write that down, at the value of the base condition, which is at I equal to log base 2 of n. This is my base condition, the value of k at which I will stop. I will get what? My work, the subproblem size has become T2. How many times will it be there? How many times T2 will be there? Let's see. This was there 2k number of times at k. What is k? Log base 2 of n. So whatever is T2 will be there 2 to the power log base 2 of n, because k is log base 2 of n. So this will be T2 log base 2 of 2 to the power log base 2 of n. Now 2 to the power log base 2 of n means it will be log base 2 of n, because 2 to the power log base 2, because both the bases are the same, they will come out, log base 2 of n will come out of that, and therefore this will become log base 2 of n. So this is my subproblem and the subproblem count. This is my subproblem and my subproblem count. Now what is my work done at the last layer? Work done at the last layer is 1. So I'll put 1, right? So it is coming from the previous stages. So I've put a dot dot dot. How many times will it be there? Again the same thing. It is 2k amount number of times, right? K is equal to log base 2 of log base 2 of n. So 2 to the power log base 2 of log base 2 of n, which is nothing but again log base 2 of n times. That means this is 1 multiplied by log base 2 of n as the total amount of work. Now we are in a position to probably do the summation exercise. So can we say that Tn is equal to summation of I equal to 0. Now we will go till 1 less from here, right? That is still where we will get the pattern, and then this individual layer of last base condition work will be there. That's how we have been doing all the problems. So this will be log base 2 of log base 2 of n minus 1, 2 to the power of I, because that's what we have got here. Every time we are getting 2 to the power k, which means 2 to the power of I. Here also we got 2 square, 2, 1, so 2 to the power of I. Right, so we will say here 2 to the power of i's summation, plus here we have got log base 2 of n. That is our base condition. Now let us take m as log base 2 of log base 2 of n minus 1. This implies that we are now in a position to call out our GP, which is this now becomes let's qualify this as a sum, then we can write it as such. So we'll say that our sum GP, which is this part of the problem, right? This is our part of the problem, which is our sum GP. So sum GP is equal to sigma of I equal to 0 to m, and this will be r to the power of I, right? That's what our problem would look like. Here r is equal to 2 and m is equal to log base 2 of n minus 1. We have written it here also. So my SGP will be equal to x or r to the power of m plus 1 minus 1 by r minus 1. And I told you that earlier case I took 1 minus r to the power m plus 1 because r was fractional. Here r is not fractional, r is 2. So I'll take it to the left side. So this is 2 to the power of log base 2 of n minus 1, right, which is divided by 2 minus 1. So 2 to the power of log base 2 of n minus 1, and this means that can we use this identity, a log base b of x is x log base b of a, right? If that is the case, then we can definitely write here a is equal to 2, b equal to 2. Therefore 2 log base 2 of n minus 1 can be written as log base 2 of log base 2 of n of log base 2 of n, and that's going to be the simplification. 2 log base 2 of n, because this is 2, the bases will cancel out. You can apply this identity also, and we can get to that. Log base 2 of n, and then this would be what will be there. So this is our final GP solution, right? Which means our Tn is equal to, if you remember here, Tn was this GP plus log base 2 of n. So Tn was this GP plus log base 2 of n. So we will get log base 2 of n from our summation. 1 minute. 1 minute. Acha, this is 2 log base 2 of n minus 1. So this should be minus 1. That's what I was thinking. Why is it coming the same? Okay, so this was 2 log base 2 of n. I just said that I will simplify it based on this identity, this portion, right? This portion. So then minus 1 is still there. So minus 1 I have put here. So my SGP is that. Therefore my Tn becomes log base 2 of n minus 1 plus log base 2 of n. Now which is bigger? Of course log base 2 of n is bigger. So dominant term is this, which means our Tn is theta of log base 2 of n. That's going to be your branching wala solution, right? So that's on this particular topic. That brings me to the end of those 3 things that we wanted to discuss. Now we have already discussed this. In the balanced branching. We have discussed this in the transformation. We have discussed this in the unbalanced branching. And all of these have come multiple times in your examinations. Let's talk about this now. And this is going to be the same thing. And it's just going to be a practice. There's nothing much you will newly learn here. But just a practice in terms of how things are getting done. So let's start with we can do it in any method because there is no method that is mentioned as such, right? So we could adopt any method for that matter. Now we will adopt the recurrence tree method for this, right? The complexity relation is this. Have they told what it is? Okay, plus n. Now ideally speaking, this if it is a MCQ or it is a fill in the blanks, you should be applying Master's theorem for it, not all these lengthy methods. Master theorem next class we will do. You will understand that it can be done in 30 seconds, right? So that's how easy it would be with Master's theorem. But for now, anyway, we'll have to do the long methods before we get into the master method. Let's do the long method here. Recursive call, and then we have work tree, and then we have the sum of work. So at I equal to 0, my recursive call is Tn, my work is coming as n, right? So my work is n and my sum of work is n. At I equal to 1, my Tn gets broken down into 2 n by 2s. So it becomes Tn by 2 and it becomes Tn by 2. And therefore we will get what? We will get n by 2, 2 n by 2s as the work also. So we'll get an n by 2 here, we'll get an n by 2 here. And if we add this up, we will get n, right? Or we can say that we are actually getting n by 2 2 times, right? We can say we are getting n by 2 2 times, just to see if we can get into some pattern, which anyway is n, we know that. At I equal to 2, this will break into 4 parts. So n by 4, n by 4, n by 4 and n by 4. So this will therefore become n by 4, n by 4, n by 4 and n by 4. And this will be 2 into n by, in fact 4 into n by 4. Which is again equal to n. So this is how it will move. Now are we in a position to find out the pattern? I told you, right, after I equal to 2, find out the pattern. Of course we have a pattern here. So this will imply what? T n by 2 to the power of 2. How many times? 2 to the power of 2 2 times. That's the pattern. And this implies what? This implies n by 2 square. How many times? 2 square times. Right? So can I, this one, let me see this. Can I write this as 2 square n by 2 square? Can I write this as 2 1 n by 2 1? Can I write this as 2 0 n by 2 0? Of course I can write it, and hence I'm getting a pattern of this also, right? So now I am in a position to start my k, right? So can I therefore write I equal to k? For I equal to k, my recursive call will be t n by 2 to the power of k. How many times? 2 to the power of k times. And this particular n by 4 will actually become n by 2 to the power of k. How many times this will be there? It will be there 2k times. Therefore this becomes 2k into n by 2k, which is matching with our pattern here. So now that we have this, we are happy. I don't think we need the left hand side. We have got the right hand side with which we can now create the summation. But still, if we can create the left hand side, we will still create the left hand side. So for the left hand side to be created, we now need the base condition, which says t1 equal to theta 1, which means n by 2 to the power k is equal to 1, which means n equal to 2 to the power of k, which means that k is equal to log base 2 of n. So with that, I can say therefore that I equal to log base 2 of n. At log base 2 of n, the things will stop and t n 2 to the power k will become 1. So this will become 1. How many times this will go? N times. Why n times? Because if this goes 2 to the power k times, I have just established k as log base 2 of n or 2 to the power k as n, right? So this will go n times. 2 to the power k times 2 to the power k is n, therefore n times. T1 will go n times. And theta 1, whatever is here, right? Theta 1, whatever is here, theta 1, whatever is here, will go how many times? Theta 1 will go 2 to the power of k times, which is actually equal to n times. Let's not write k in the last equation or in the last line. We are supposed to avoid k, and that's the whole point. So we will not write this, we will just say n times. And I hope you understand why n times, because we have 2 to the power k here and 2 to the power k is n. That's why. So this is becoming what? N times of theta 1. So now we can actually sum it up. And I don't seem to have space. So let me create some space and then sum it up. Space is created. Now we will complete this problem. So we have created the tree. Now we'll do the sigma part of it. So what we'll have to do is, from a sigma angle, what do we know? We know that Tn can be written as sigma of, let's see the top part. What are we doing here? See, at every layer there is an n. 2k cancels out. At every layer there is an n. While the pattern is there, it is of no use because we can just take directly n. Right? So there is no dependency on I for that matter. So I equal to 0 to log n minus 1, and at each layer that work done will be actually n. How many times this n will be added? 0 to log n minus 1, because your last layer is at log base 2 of n. Previous to last layer will be log base 2 of n minus 1. So we have n as the work done for each layer. How many layers? Log base 2 of n minus 1. So sigma will be looking like this. Sigma will be looking like this. Sigma of we will say n, and then I equal to 0 to log base 2 of n minus 1 plus n theta 1. This is the base condition. If you remember, this is the base condition work done, which is n theta 1. This is the one that I am talking about. So that becomes easy to solve now, and this n theta 1 will be equal to log base 2 of n times is what we will do. So this will be log base 2 of n times of n plus n theta 1, right, which is equal to, so therefore Tn becomes equal to theta of n log n, because your dominant term is n log n as compared to n theta 1, and that becomes your solution to this problem. So same kind of problem, because the division is the same, to Tn by 2. Only thing that changes is the work done. So work done, that layer will only change, rest of the things will remain the same. Yeah, we have one more problem, I guess. Yes, so this is 2Tn by 2 plus n. Didn't we do this just now? Yes, we did this just now. So 2Tn by 2 plus n is done, 2Tn by 2 plus n is done, 2Tn by 2 plus n is done. So we have this problem to do, which is the last problem in this particular lecture. So let's do this problem also. Again, it's an easy problem to solve. So it's given that let's write the problem. It's given that Tn is equal to 8t n by 2 plus qn. Now it's also given that if n is greater than 1, Tn equal to p if n equal to 1, and that's your base condition. You have to figure out that's your base condition, because you can therefore write that T1 is equal to p, isn't it? It is said if n is equal to 1, Tn equal to p, that means n becomes 1, T1 equal to p, and that's your base condition, and p is a constant. So now you can actually get into your standard stuff, which is writing the levels, writing the recursive call, then writing the work time, and then the sum of work. So we have I equal to 0, we have this as Tn, we have this as Qn. Qn is the amount of work. That's why we are writing Qn. This is Qn. At I equal to 2, we can say that there are 8 times we have to divide, right? So we will divide Tn by 2. We will also get one more Tn by 2, and this we will keep on doing 8 times, right? And here also we are doing the same thing. We are doing Qn by 2, and this again Qn by 2, and this entire thing we are doing 8 times. So we are getting 8 Qn by 2, which is actually equal to 4 Qn. Now at I equal to this is at I equal to 2. Now for I this is for I equal to 1, my bad. For I equal to 2, this is I equal to 1. For I equal to 2, we will get what? We will get Tn by 4, and Tn by 2, if Tn breaks down into 8 times, Tn by 4 will also break, or this Tn by 2, this Tn by 2 will also break down to Tn by 4, and this will happen 8 times. Right? So this will happen 8 times. So the other Tn by 2 will also break to Tn by 4. That will also happen 8 times. And how many Tn by 2s were there? 8 Tn by 2s. So this will happen, this will be there 8 times. Right? So total, how much did we get? We got 64 times Tn by 4. So each of Tn by 2 whenever we break 8 times. We had 2 here. Each of these 2 will break. And sorry, we didn't have 2 here. I showed 2 and I said 8 times. So we have 8 here. Each one will break 8 times and there are 8. So 64 times Tn by 4. And then we will have this to Qn by 4 8 times. This to Qn by 4 8 times. And this entire thing therefore will be 64 times. Which means we have 64 into Qn by 4, which is 16 Qn. Right, so that's what we will get from here. Now, are we in a position to actually call out our patterns, because we have finished I equal to 2. Let's see that. Okay, so this is easy because right now we can therefore say that this is, we have to qualify this 64 first with respect to this I equal to 2. So can I say this is 8 square? So 8 square times is what is happening here. This 64 is 8 square times. So this 2 is accounted. And this n by 4, you know how to do it. How should we do it? We should say 8 times t n by 2 square. And here what will we do? We will say Qn by 4 means, this means Qn by 2 square 8 to the power of square times. Right, so that's what we will say. So this brings me to the generic form. This brings me to the generic form where we can therefore say that okay, before the generic form, let's see where will it stop. Right, so where will it stop? It will stop at we had established something here, T1 equal to P. Yeah, so T1 equal to P is where it will stop. That means okay, let's write the K first and then we'll find out when to stop, right? So yes, of course, we had generated this pattern. Now it's time for us to create this for K. Are we finding any pattern here? Let's see. So this is Qn. Can I say this is Qn? Because this 16 has to have some pattern with this 2. Right? So can I say that this is equal to Qn into 4 square? Then I can say this as Qn into 2 square, or rather 4 1. Qn into 4 to the power 1. I can say this as Qn into 4 to the power of 0. So yes, I'm getting a pattern. Now, what will I write Ik as? Let me write it here itself. Let's say at I equal to K, right? I equal to K, what will happen? We will have T n by 2 to the power of K. This will go 8 to the power of K times. Because for 2, if it is 8 square, for K it will be 8K. And then this is anyway you know. So Tn by 2 to the power of K. And Qn by 2 square will become Qn by 2 to the power of K. Qn by 2 to the power of K. How many times it will happen? 8 to the power of K times. Therefore, we have 8K multiplied by Qn by 2 to the power of K as my total summation of work done, which means this is equal to 2 to the power of 3K Qn. 2 to the power of 3K Qn by 2 to the power of k. I just broke down that. So that is equal to 2 to the power of 2k qn, which is equal to qn into 4k. So see, I reached the same thing. Qn 4 square, Qn 41, Qn 40, Qn 4k. Right? I reached the same thing. It will come like that only. I needn't have done all of this on the left side, which is what I was trying to tell you, that one approach is take the right side and find out the pattern of the kth element without even working on the left side, which is perfectly fine. Right? You can say this first term and then say some number of times, or some number of times here and then say this. Of course, you have to write this first term in order to establish that. But then you can also do the way I did. When you have the possibility to do it, always do it. Only in unbalanced you will have a challenge. There also with combinatories you can do it, but that's on the discrete maths path. So let's solve this now. So for I equal to k, now we can put the base condition. Let's put the base condition here. So my base condition is that n by 2 to the power of k, because I had my at the kth iteration I was having what? T n by 2 to the power of k. That was my work sub problem, right? So this sub problem will become T1. That means n by 2 to the power k will become 1, which means k will become log base 2 of n, which means that I can substitute for I with log base 2 of n instead of k. I can put log base 2 of n for the last iteration. So this was I equal to k, right? And k is log base 2 of n. So the last iteration happens here, I equal to log base 2 of n. This is where the last iteration happens. So this means that we would be, the sub problem will have come down to T1, and this will do how many times? This will be done 8 to the power of k, and k is log base 2 of n. 8 to the power of k, k is log base 2 of n. So this will happen 8k times. And we have this as p as my, because my T1 is equal to p. We had seen that when we started this problem. So at T1, at the last layer, I will be getting p, and this p will be how many times? 8 to the power of log base 2 of n. That is how many times it will be there. So my work is becoming p into 8 to the power of log base 2 of n. And this means, this means p into 2 cube log base 2 of n, and which means that the n cube, n will come out, and then 2 and 2, because the bases are same, they will go out. So this will be p n cube, right? That's again a property of log. You will have to read log if you are not aware of it or you have forgotten it. So now I'm in a position to probably say that what is going to be my ptn. My tn will be a summation of I equal to 0 to log base 2 of n minus 1. By now you know my last iteration is log base 2 of n. So my previous to the last iteration log base 2 of n minus 1. And all the previous iterations are going to go on for how much time? Qn into 4i. Right? You see here Qn into 4i. So that's what we will write here, that log base 2 of n minus 1, I equal to 0 to Qn into 4 to the power of I plus this Pn3, that is the base condition Pn3, which is equal to Qn can come out I equal to 0 to log base 2 of n minus 1 4i plus Pn3, which is actually nothing but this part of the problem becomes a GP, right? So this part of the problem becomes a GP, and for that can I say sum of GP is equal to sigma of I equal to 0 to m r to the power of I, where r is equal to 4 and m is equal to log base 2 of n minus 1, and therefore this is equal to r to the power of m plus 1 minus 1 by r minus 1, and that becomes equal to 4 log n. That is what it is. R is 4 and m is log n, plus 1 minus 1. This is log base 2 of n minus 1. So 1 cancels out, and we have this 4 minus 1, which is 4 log n is again 2 square log base 2 of n. 2 square log base 2 of n minus 1 by 3. So that is written as n square minus 1 by 3, which implies Tn is, therefore, this is SGP. So our Tn was different, right? It has to have Pn cube. So it will be, and of course it had this Qn also, Qn angle there. So Qn multiplied by n square minus 1 by 3. I hope you understand why this became n square. 2 square log base 2 of n, you have 2 and this log base 2. So that is the property with which n will come out. The to the power 2 will still remain. So this becomes n square. So this is therefore equal to Tn Qn n square plus 1 plus this Pn cube is there, and which implies that if you see this, the highest power will dominate, which is n cube. Therefore Tn will be equal to theta of n cube, and that's your solution to this problem. Most of the problems are easy, same style, same logarithmic formulas are coming here and there. So I hope you can understand this. Let's see if any other theoretical questions are there. So there will be some theoretical questions, couple of them I think, and in those theoretical questions you will see that we are talking about the recursive nature of the problem, the recursive nature of the problem solution, what is the advantages of recursive tree. All of that I have put it in one place. So let's see what that is, right? So this is the problem that had come multiple times, which is short notes on recursion tree. Before this, there will be one more problem I'll tell you, but then in order to understand this, just figure out that in order to explain a recursion tree, you will have to talk about the nodes and what these nodes represent for you. So these nodes in the tree, what they represent for you, because each node, as I have been telling, represents the cost of the single subproblem. So you will have to define the tree first, right? Short notes on recursion tree means define the tree, and the most important part is the node because it has the work, and the total cost is the total sum of the work in that node. So define the components, the node, the branches, the levels, the leaves, because you are asked to talk about the recursion tree, talk about the tree, and how to solve using recursion tree, because if this is 5 marks, this will not fetch you 5 marks. So why is recursion tree used? To solve a problem, right? That you find out the cost at each level, determine the height, and sum all the levels till that height. That's what you do. That's what we have been doing. And then take an example, just like we did for Tn 2Tn by 2 plus n, which is on your merge sort. You take that example and explain that using the tree, right? So that's how this problem should be attempted. Then there is this concept of why recursion tree is much better than the substitution method. Of course, recursion tree, you can see the nodes, right? You can see the nodes, and you can be intuitive in terms of understanding how the nodes are behaving, because you know that from the right side you can sum up all the work done and then add the base condition. So the ease of summation is also there, right? And if you have an unbalanced tree, it is much easy to track asymmetry, because for a substitution method, tracking asymmetry is very difficult because all of them get added together and the pattern gets lost. But here you can actually keep the pattern separate, because you know that there will be one node which will flow quicker than the other by looking at the tree itself. So that is how this question should be attempted. Yes, with that I come to the end of this particular lecture. I think it has been a long lecture, but I think it's worth it, because with this, if you actually hear the entire video of this, I'm sure you will get to know how to solve recurrence relations using recursive trees and also the substitution method for complex problems as well as easy problems. Outside this, I don't think anything else is needed, but of course feel free to browse other internet literature, but then this is what I felt would be most optimum for you. Thank you. Till the time we meet next for Master's Theorem.